Thanks. I'll begin with a word of prayer. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray you be with us today. Help us to, again, Lord, glorify you in what we do, Lord. In your name I pray. Amen. So as you guys know, you have a test Thursday, right, Paul? Where's Paul? I'm sorry. I'm an idiot. Let's see here. Campbell, Nathaniel, Mark. No, Mark. Let's see here. Stephanie. So guys, do you have any questions while I'm doing this very exciting activity? Evan, it's right there, back behind you. And also, he's the other direction behind you. Going, what do you know? That way. Let's see here. So what I did was I just stapled together Jang? Oh, I just stapled together the actual quiz 9 with the other quizzes we've had lately in just a one big packet. These aren't particularly in order. I just sorted your names and put them all together so you'd have your work back again. Now, so if you, Michael. So you can go back and, we looked at the solution to these problems on the day the problem were given for the most part, right? And so you can kind of compare what you did to what we found the solution to be there if you want to. Sutton? Now you're there. All the way to the back. Oh, sorry. That's funny. Sorry. I'm too amused by that. Let's see here. Hand that back to Aaron. He's right behind you. No Joseph. Grant. All right. I got that out of the way. So again, I err on the side of I just want to give you credit for being here and trying. So I gave everybody a good score, and I do think the one you guys just turned in, the quiz 10, that one will be graded more, with more detail. I'm going to send that to the grader, and you'll get it back hopefully next week if everything goes as planned. All right. So we have a test Thursday, right? What's it on? What's that again? Chapter 12, right? So that means the convergence and divergence of numerical series, right? The kth term test, limit comparison, direct comparison, geometric series, ratio test, root test. What else do we have? Integral test. The telescoping series example, remember those? It's been a while since we hit those, but they're there. All that fun stuff. And then the majority of the test will probably be, it's probably, I don't know, I'm not sure exactly the breakdown, but there will definitely be a lot of power series on the test for sure. I think that's one of the important things we're learning in this course. And I want to make sure you leave this course with the ability to actually approximate functions with series, especially common functions like sine, cosine, cosine, exponential, these sorts of things. Let's see here. I think what I gave you guys, let's go over the quiz if you guys don't have a particular question otherwise. Anybody have a question? You do have a question? Okay. I'll tell you what, while you're finding your question, I will start going over the solution to the quiz. I think we can do both. So, yep. Oh no, I thought I heard somebody say professor as like a question. No, just the voices in my head. Okay, that's good. Eventually, this will work. Come on. No, that should work. Oh, there we are. So this is test 3 from last time I taught the course. And we're more or less the same structure here. So, this is I'll post this solution in Blackboard hopefully later today. But here's problem 1. Find if this series converges or diverges, like inverse tangent k. Okay, so as k goes to infinity, that goes to pi over 2. Not 0, diverges, kth term test. Simple as that. This one is essentially like k cubed over dividing the square root of k, because this and that are tiny in comparison. So this is basically like a 3 minus 1/2. This is like p equals 2.5. So either by limit comparison or direct comparison, you can see this converges. So like the first problem I gave there, I just gave, does it converge or diverge? No partial credit. This one I asked to actually have work show that this is a convergent series. So I use the ratio test, right? And do the algebra. Works out to a 1/4. So that converges by the ratio test. Here's a, again, I'm going to post this for you guys to look at. But, sum of the series, find the sum of the series. If I ask you to find the sum of a series, that means there's pretty much 3 things that could be possibly the case. It's either telescoping like this one. It's geometric, right? I guess the other possibility is it could be like a sum of geometric series. We did an example like that early on. That's also possible. And then more recently, the weird last problem on your quiz, right? Where it's actually the power series of a specific function evaluated at a point. That's the third kind of sum of a series. Basically, it's one of those 3 sort of patterns, either telescoping, a play on geometric, or it's an evaluation of a known series at a point. That's pretty much the only 3 things we know how to do in order to actually find the sum of a series, barring artificial problems, right? Like if I tell you the nth partial sum of a series is something, you can actually take the limit of that nth partial sum, and whatever it works out to, well, that's the limit of the series, fine. Excuse me, that is the sum of the series. But here's a geometric one, right? A lot of people couldn't do this right last time I did this. A lot of people got this problem wrong. There's really no need for that. People who get this problem wrong are being careless. And you need to be careful, right? Laws of exponents, you have to sort through it and make clear in your mind, how do you identify the A and the R in a geometric series, right? So this, I had to do a little bit of algebra to realize that this is 1/8 times 2/49 to the k. So I pulled out the 2 to the minus 3 and rewrote 7 squared as 49. So 49 to the k over, dividing into 2 to the k. That's 2 over 49 to the k. And, I just was checking it here. K equals 0 gives me that. So that tells me the 0th term is 1/8. The 0th term should be, quote unquote, A in the geometric series, A plus AR plus AR plus AR squared and so forth. So take a few minutes to really cement in your mind, how do I specifically figure out A and R in a geometric series? It may be something you're kind of slopping over. You should really make sure you have that down carefully, because this got a lot of people last time I taught the course, and it shouldn't have, because this is an easy problem, right? It's just kind of got a little bit of ugly arithmetic, but really it's an easy problem. And then, check it out. Does this look familiar? Yeah, it's your quiz, right? Oh, I wonder if I fixed the typo on the quiz. Oh no. Oh no, please tell me. Was there a typo on your quiz? Where were we? Oh, good, I fixed it. I accidentally had an N here on the test, which was unfortunate, but I did that on purpose to see if the students are paying attention, of course, as always. But let's see here, where was I? Where did my solution go? No, where? Oh, sorry, it's just hiding in plain sight. Sorry. All right, so this one, define the interval of convergence and radius of convergence. Oh, I'm sorry. I used these abbreviations. I don't know if you guys, did you guys know what those meant in the quiz? You guys, when you have some question like that, you can ask me. Like, it's totally legit if you don't know what.
I think you wrote it in the notes when you were on the board. You wrote IOC and ROC.
Right.
It was pretty easy.
Okay. I just, in principle, like, suppose you come across something like that in a test. Don't sit there and, like, just ask me if you have that kind of misunderstanding. I don't mind, for the most part. I mean, if we're in a higher class and you ask me what's the definition of linear independence in the middle of like a linear algebra test, I'm just going to be like, go away. That's a different thing. This is just terminology here. Okay, anyway. So the ratio test gives us this, right? And so if that's less than 1, then we get convergence by the ratio test. So in other words, we need x minus 3 less than a half. That describes the open interval of convergence. Basically, we're guaranteed 2.5 to 3.5. We have to check the endpoints, all right? So the one endpoint is an alternating series. The other one is a harmonic series. We get this one, we lose that one. So in short, the interval of convergence is 2.5 included, 3.5 excluded. All right, and any questions about this? So generically speaking, this is what you have to do for if you just have a power series, you don't know where it came from, all right? Ignore, if the power series is constructed from a geometric series, you don't need to go through all this, right? For example, if I have the power series, some, x to the 3n, n equals 0 to infinity, right? Which is what? 1 plus x cubed plus x to the 6th plus dot, 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 right? Well, this is exactly geometric with 1 over 1 minus x cubed, right? So I know that this is only good for what? Minus x, well, excuse me, not minus, but just x cubed less than 1. Which, by the way, says that the absolute value of x is less than 1. So the interval of convergence is minus 1 to 1. I can do all of that without a ratio test, without checking the endpoints. Why? Because this is a geometric series, right? So it's part of a very special, let's say, elite class of series, which we know something so much more about. We already know what that is and what it's where it converges. But something like this problem here, well, this is not geometric, and so we're forced to use tools. We're forced to use the ratio test to find the open interval of convergence, and then we have to check endpoints by explicitly plugging in the point and using the beginning of chapter 12 stuff. And usually it's the alternating series test and like a P series, like a lot of times, a lot of examples use that. Any questions about this? Sure. It's because we worked out the ratio test, right? The L from the ratio test works out to, let's see, what was it? It worked out to 2 times the absolute value of x minus 3, right? Ratio test says we get absolute convergence, provided that this is less than 1. I mean, because we're testing the absolute value of the series, term-wise. And so if that's the case, then this gives us the absolute value of x minus 3 is less than 1/2. What this means is that the distance from x to 3 is less than 1/2. That's the way to understand that inequality. Here's 3, here's x. So here's like 3.5, here's 2.5. That has to be the picture because this is, that. That's the distance from x to 3. The absolute value of a difference between two numbers is a distance. So that's why the radius is 1/2. I am getting better. I assure you. I'm not entirely convinced myself, but anyway. Number 6. use geometric series to find the power series for this function. Well, this is just it's not quite, I would say it's just plain, but that 3 is cramping our style, right? So you got to do something about the 3 because geometric series is a over 1 minus r, right? That's what we get the formula for. So I have to create a 1, right? There has to be a 1. And so factor 3 out, that gives you a 1. And then you've got your a as being x squared and your r as being x squared over 3. So geometric series result here, when does that hold? It holds when the radius is less than 1. The absolute value of the radius being less than 1. But this gives me x squared is less than 3. Take the square root of this, you get the absolute value of x is less than the square root of 3. That says that the center is 0 and the radius is square root of 3 in this case. So it's like x minus 0 less than root 3. So that's playing the same role as a half did over there, right? So anyway, there it is. F of x is 1 over 3 to the, let's see here, k plus 1. See, this gives me 3 to the k. That gives me the plus 1. And then that's x to the 2k plus 2. Does that make sense? So this is just a straight, pretty much straight geometric series question. This was, I guess, your problem 3. So use geometric series techniques to find the power series for this, centered at x not equal to 1 in sigma notation. Let's see here. So what I do is I create an x minus 1, right? Well, first of all, I differentiate, because I know differentiating log gives me like a reciprocal function, which I can go geometric on, right? So this is the standard trick for a log. We differentiate. That gives us a reciprocal function. I add and subtract 7 here to make the kind of thing I want, which is an x minus 1. And that gives me this, but then I have to factor out the 10 to create the 1. And so I've got 7/10, 1 over that. That's geometric, and then so I go to the geometric series result, clean things up. Now I've got a series for the derivative. And so then I integrate, and that gives me, this is a series for the logarithm. But if we plug in f of 0, what should we get? Well, f of 0 should be log 3. Now this series starts at x minus 1. And, oh man, that's no bueno. He's no good. Sorry. No. If you plug in 0 into here, this ain't 0. No. This logic is wrong. Like, this constant might not be log 3. The solution is no good. Let's see here. I don't think it's good anyway. Instead, when we get to here, what should we plug in? We should plug in f of 1. See, f of 1 is what I should plug in, because f of 1 makes this go away. Right? So plugging in 1 will give me c plus 0. See? Sorry, that was awful. Oh, I guess you could have thought of it several different ways. But anyway, you see what I mean. I'm sorry, I can't stop. So f of 1 is also equal to the log of 3 plus 7, right? So this solution is almost, well, it's not almost, it's wrong. It's wrong, admittedly wrong. So don't tell my students from last semester. Let's see here, c equals to log 10. Why didn't they tell me about this? Log 10. Maybe they did. They probably did. So that should be log 10, right? This should not be log 3. This should be log 10. Sorry about that. You see why? Do you see the error of my ways? When I plug 0 in, right, I'm assuming that f of 0, well, f of 0 is log 3. That's true, right? But f of 0 is not c plus 0. When you plug in 0 to this, you've got minus 1 to the n plus 1, all this junk. That's some complicated series. Who knows what it works out to? But it's not 0. So what you want to do is you want to plug in the number that makes the series go to 0 so that you can isolate the c, as to link it back to the function that you differentiated and then integrated, right? So we got to be careful with this geometric series trick, because the process of differentiating and then integrating back adds a constant, which brings in an ambiguity that you have to be careful about, right? More careful than I was in this solution. A lot of times, this constant has worked out to 0 for us, but that's just a quirk of the examples we worked in class, right? Do you guys get this one? So here we have a power series. Where is it centered? 2, right? We're also given that it converges at x equal to 0 and it diverges at x equal to 5. So here's my picture. It centers at 2. We've got this point of convergence at 0. We've got this point of divergence at 5. So everything past 5 has to diverge. That's the theorem. And let's see, how far are we from? We're 3 units, right? So 3 units this way gives me -1. So everything past there also has to diverge. -1 is up for grabs. It might be a point of convergence or divergence itself. So the largest possible interval would be -1 included to 5 not included. The smallest possible IOC would be we just pick up this point of convergence and then we go symmetrically on the other side. So this is 2 and then 2 of the other side. So 0, 4 would be the smallest IOC possible with this data. Are you guys starting to get it? These are usually mystifying to most people at the start. I hope you're starting to understand. We'll find out Thursday, I guess? Yeah? I'm sorry. It's too soon. Yes, here. Okay, find the first 3 non-trivial terms in the power series at x not equal to 1 for this. Why did I ask this? Just tedious. First 3 terms, and this x squared makes my stupid adding and subtracting 0 trick a pain. The sine of x, if I add and subtract 1, it's still a pain. So I've got a trinomial times a binomial, just direct algebra. Very, very tedious here. It's just less work to just plain old differentiate and apply Taylor's theorem. You're like, but you've been selling the opposite story in all of our examples. I know. Maybe this was a mean question. I don't know if I was intending it to be such, but it probably was. Anyway, it is something you should be able to do. So you just got to pick your poison, right? Here I picked the Taylor's theorem directly. Excuse me. What am I doing here? Why am I doing this? Huh. Oh, I guess I just did, but I didn't say I wouldn't want it. Oh man, I actually multiplied out the trinomial and the binomial. See, I don't know. I mean, this is a solution. What I got here is a solution, right? Fine, there it is. But I wonder, for this one, if it's not easier to just plain old look at g of x. So you got f of x, right? Is equal to 1 plus x squared. Sine of x. So the other solution I'm describing, let me write on the board. So here's f of x, right? It's given. So that says f of 1 is what? Where are we centering it? At 1, right? So what is f of 1? 2 times the sine of 1, right? What's f prime of x? How many terms am I supposed to find? First 3 non-trivial terms, right? There's 1 non-trivial term. So this means I only have to calculate the first and second derivatives. That's a pain, but it's probably easier than what I've done here. So let me show you how to be a little bit more clever than my current solution. Differentiate this. Now I do presuppose that you know how to differentiate. That is true, usually, for most of you. Although every once in a while, you guys will like give up on one tenet of differentiation just for one part of a problem, but not on the others. So like, it's funny, people will like just give up on something they know for just one problem to make the problem seem simpler. I don't know why people do this, but they do it. Anyway, so there's the first derivative. How about the second derivative? I mean, you gotta take your medicine here, it's a pain. But this is, I think this is easier than the pain I faced in the problem. So f prime prime of 1 is what? It's 2 sine 1. Oh, yeah, subtract 1. So it's just sine 1. Just get me to the point here. Sine of 1. I'm combining this and that. 2 minus 1 is 1. And then this gives me 2 plus 2, 4 cosine 1. So therefore, f of x is equal to, of course, f of 1 plus f prime of 1 times x minus 1 plus 1/2 f prime prime of 1 times x minus 1 squared plus dot 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 dot, right? And so that is actually equal to 2 sine 1 plus cosine of 1 plus 2 sine 1 plus cosine 1 times x minus 1 plus 1/2 sine of 1 plus 4 cosine of 1 times x minus 1 squared. I think that's probably an easier way to find the first 3 non-trivial terms here. What do you see something else, Mr. King? You stop me! You guys gotta stop me! What did I do? What would I do wrong? The first derivative?
1 plus x squared times cosine of x. You just pull that.
Oh. Well, you guys, go on. Fine, then, nah. This is wrong. Well, now I gotta go back. Why you should interrupt me much earlier. Oh. You tried to. I was too carried away. All right, fine. So this is, it makes it worse. One. So that's basically it for that step, right? So that puts a 2 here. Which puts a 2 here. Why? Sorry, I'll get over it. So that's right. This is right. That's right. This is supposed to be 1 plus x squared cosine x. And, sine x, right? Sorry.
And then the same thing.
So those, so we just get 4 cosine 1 here? Well, that's nice. Actually made it nicer. Well, I'm sorry I didn't hear you guys. You guys got to be like more aggressive in your interrupting. Is that what I got here? 2 sine 1. Aw, man. I got no cosine 1. Oh. You guys, look. Here. Is this right?
Yeah, well, in your thing up here,
Look. F of 1. F of 1, what did I say it was? 2 sine 1, right? So I'm supposed to write 2 sine of 1 as my constant term. Then the derivative, 2 sine 1 plus 2 cosine 1 times x minus 1. It's good. And then this one, 4 cosine 1 times 1/2. In other words, this is 2 cosine of 1 times x minus 1 squared. Right? Okay. And so forth. Is it the same now?
Yeah.
Yeah, we got our 2 sine 1, our 2 cosine 1, plus 2 sine 1 times x minus 1, and then these cancel, right? 2 cosine 1 times x minus 1 squared. I wrote it like this so that when I was grading, I could see what people did. But anyway, as you can see, however you do this problem, you must be careful. Otherwise, things will happen to you. All right. The next term here is just, I mean, you could do this lots of different ways. You could also apply Taylor's theorem and differentiate secant of 3x, right? But if you do that, you got to do it right. Secant and differentiates the secant tangent. Do you know that? Some of you didn't know that last test. I hope you've learned that. But anyway, here I use division of series because I think it's fun. And so this works out to 1 plus 9/2 x squared plus 135 over 8x to the fourth through the usual subtraction algorithm. Of course, you could derive these by looking at f of x equal to this, right? So like, I could calculate f of x. I could calculate f of 0 would be 1, right? 1 over cosine of 0 is 1. That's this one. F prime of x, the next term, right? What's f prime of x? In this problem, it would be d dx of what? Secant of 3x, right? Which would be 3 secant 3x tangent 3x, right? And so if I plug in f prime of 0, I get 0, right? And so that's why there's no what? There's no linear term here, right? So I undersold it. Do you have to take 3 derivatives here to find the first non-3 trivial terms? No, it's much worse than that. To find the first 3 non-trivial terms, you have to take 4 derivatives here. So division of series is important because you can't always work around things by Taylor's theorem. Did you guys get this one? I hope you got this one. Or if you didn't get this, I hope you can see how to do it after we talk about this for a minute or two. So all you got to do is just convert this to a power series. So 1 over 2n factorial, 3x to the 2n. That's just substitution of 3x into the Cauchy series. This x to the 5th rides along. And then you have to clean it up. You have to clean it up before you do integration. Sometimes you guys try to like integrate this and integrate that separately. Ignore the fact that the 3 is inside there. Don't do that. It's not, you gotta like change it to a power series and then do the integration. Anything else goes badly. All right, the theorem is for integration of a power series. Make it a power series before you do the integration. But there's a power series, now I integrate. So that goes to 2n plus 6. We divide by 2n plus 6. And I just clean that up. That 3 to the 2n is 9 to the n, right? And then it's 2n factorials, it remains, and there you go. Actually, I would argue this is easier than the integration you were doing on test 1. I mean, think about it, really. Isn't this easier than like a typical trig substitution? It's pretty straightforward what you do. You find the power series, clean it up, integrate term by term. It's simple as that. Don't make it more complicated. Now, if you don't know the Cauchy series, well, then you're kind of in trouble. But you should know that. Here, basically the point is this is an alternating series in this sense. And so when I do the term by term integration and evaluate, I get an actual honest to goodness alternating series. And so if I keep the first 2 terms, the inaccuracy of just using the first 2 terms as opposed to the whole sum is given by, it's at most the next term. That's the alternating series estimation theorem. 1/90th is about 0.01 so 8/9 is a good approximation to within 0.01, right? Is bueno? Is good? No? Have I made a mistake? No? Okay. I'm leery. Oh, look at this monstrosity. Yeah, so basically the game here is you got to isolate terms that have order 100, right? This is a naked term with order 100. It's just sitting there, right? That contributes a 1. That's this 1. The other thing, this has no order 100 term, right? So like cosine of x to the 4th gives you x to the 8j kind of things, and that misses the 100th power. It skips over it. We go from 96 to 104. We never hit 100. Students found a way to get this to give a term when they did this test. I don't know how they did it, but they're very inventive. More abstract than I am. They found a way to use this, but you shouldn't find anything to use here. There is no integer solution, which means it doesn't count. In other words, there is no 100th power in this power series expansion. This one, on the other hand, does hit the 100th power, right? Like the 98th power in the exponential expansion, and the x squared gives you 100. So basically 1 over 98 factorial from this term, and again the 1 from here. Taylor's theorem says all of that is equal to the 100th derivative divided by 100 factorial. And so there it is. We've done a lot of these in here. I mean, not a lot. I mean, it's probably about our 5th one, right? 4th? I don't remember. I can't count. Oh, look. I guess I didn't put this on your quiz, did I? But I thought it was important enough to put on the... I did? I did? I didn't. I think the last one... Oh, yeah, excuse me, guys. I'm sorry. Ugh. Where did I put that thing? Oh, duh. Eventually I'll learn. So for you guys, I traded up the last one. I made it this thing, right? And that was just, let's see here. If you take the sinh of x is the sum k equals 0 to infinity, x to the 2k minus 1 over 2k minus 1 factorial. Oh, plus 1 rather. Aw, man. Did I? Oh, we'll stink. This doesn't mean anything. This problem has to be thrown out. You guys all get credit for this one. Dang it. Look, guys, this is what I should have had. And what I was trying for was that this differentiated gives you cosh I mean, I was aiming for this was the kind of pattern I was looking at, and then I plug in a 3 into that. But anyway, sorry about that. You guys should have. Anytime you plug in 0 and you get minus 1 factorial, you should know that I made a typo. Minus 1 factorial we have not defined. Right? We did not do that. I promise. It only exists in this class in this problem. And there only wrongly. Or perhaps rightly, because it gave you all points. Woohoo! If I can convince the grader that no matter what you wrote there, he will give you 3 points. I'm sorry, Travis. We seem to have not got to your question. But there is still tomorrow. Yeah.